I'm going to show you guys how to use XGBoost in R, and as an example, we're going to do a Kaggle competition. And if you don't know what Kaggle.com is, it's a place where you can download datasets, and they always host a bunch of competitions, such as the ones here, with cash rewards. And so the one that we're going to be using for this example is a $50,000 prize pool. Here's the pricing breakdowns right here. And in this competition, we're trying to create a model to predict how well one Monte Carlo tree search variant will do against another in a given game. So basically there's two computers playing each other in, say, a game of chess, and there's certain conditions for each match that is played, and we know these conditions. The data gives us these conditions, and our job is to create a model that, based on those conditions, those features, we could say which Monte Carlo simulation has the advantage in that game. So I'm going to host all of my code on GitHub. I'm going to walk through it all, the entire process from start to finish, from creating the project to submitting it to Kaggle. So here we go. The GitHub repository is here. This is the URL. So Enamato18/YouTube-ML-competition. If you want to use this repository, go ahead. If you're using Git with R, you can just copy this little HTTP here. And now we're in RStudio. You go to new project, version control, Git, and then we just copy and paste that URL right there and hit create project. And once that is done, you should have a fresh RStudio here. You can see the directory that we're in here. This is where all our files will be. So for this competition, they provide you with the training data, and they give you a bunch of rules and what's in the data and everything. But what you want to do to get started here is you can download all of this data. It looks like it's about 1.32 gigabytes. So download all that. I have already downloaded all of this right here, so I'm just going to go into that folder. I'm going to copy all of this. And then this here is my project directory, my R project directory. I'm going to create a new folder called data. And I'm just going to go in that and paste everything in there. So now I have all of the Kaggle competition data inside of my project. So now let's get into some of the code. Let's create a new file here. I'm going to zoom in so you can see it better. Let's just say that df is equal to read CSV, and then the file path for that is data train CSV. So we do data train CSV. Run that. It's going to take a little bit because this is a huge file. By the way, I'm doing all of this in R. You can do this in Python as well. The methods are similar. The syntax is just different. You can do it either way. So before I go any further, we can really break this entire process down into 4 big steps. So our first one is gather all the data and explore that data. Let's get an idea of what we even have. The next step is to pre-process that data and make sure we get all of our data in a format that we want it as. That's like, we could also do things like feature selection here. And then our third step is going to actually be building the model. And our fourth step is going to be to view those results, kind of see what we got going on. And well, I guess an optional fifth step then is to go back and really start reworking things, fine tune the model, do better for feature pruning, those sorts of things to really improve your results. And we're going to walk through all of it. So we've read in our data frame here. Let's take a look and see what's even in here. So it looks like there's ID columns, there's game set rules. This is the name of the Monte Carlo simulation. So this was agent 1 in this situation. This was agent 2. And then it looks like it moves into a ton of rules for each game. Another way we can get a glimpse of the data here is if we do str and then df. So that'll give us the structure of the data frame here. So it looks like we have a lot of integer columns, some character columns. I like to have everything as numeric columns. So I'm actually going to go ahead and change all of these integers to numeric. So what we're going to do here, we need the dplyr package. So we do library dplyr. If you don't have that package installed already, you go to tools, install packages, and then you just type in dplyr. It should pop up. You just click it, install. Okay, so turn integers into numeric. So I'm just going to say df numeric equals df, and this little operator here is a pipe operator, so we're passing our data frame to whatever I type next using mutate if. So we're basically just going to modify every column where a condition is met. So everywhere where it is an integer, we're going to say as numeric. So if we run that, and now we do structure of our df numeric, you can see now that instead of integers, we have numeric column values. So that all worked out okay. So you can see that we have 814 variables, which would be a ton of features. So immediately let's just kind of start and try to get rid of some of these. So what we can do is look for any columns that have entirely the same value for the entire data set. So let's say that this hints column here is just zeros all the way through for every entry. Well, that doesn't have any significance to us at all. If there's no diversity in a column, then it holds no value for us. The machine learning model is not going to do anything with it. So we just remove those. So the first thing we want to do is identify all the columns that are just uniform. So identify uniform columns. To do that, I'm going to say unique I'll say uniform vars is equal to lapply. And lapply is just going to, so we're going to feed it our data frame. So this is going to apply whatever function now that I type in to every single column in the data frame. So let's say if we have a function of x, and that function is just going to be length unique x greater than 1. So what this is doing is it's going to take the unique values of each column, and it's going to say if the length of that value is greater than 1, then it's going to return true. If it's not greater than 1, it's going to return false. Actually, let's, instead of saying greater than 1, since we're trying to find all the uniform variables, let's say is equal to 1. Oops. So now this is saying if there's only one unique value for that entire variable, then this is going to return true. So that's a uniform variable. And if this is not true, then it's just going to return false. So let's run that. And let's just take a look at that. So I'm going to type in uniform vars down here. Right now it's in a list it's like in a named list object, which is okay, but I don't really want that. So I'm going to do the pipe operator here. And I'm going to say unlist. And that's just going to take all these values out of the list. So I'm going to run it again. And now if I say, let's check it out again. Oops. Uniform vars. So now instead of, it's not a list. These are still like named logical values, but it's not in a list anymore. So that's good. That's what we wanted. Okay, so now what we want to do is we want to remove all of those values. So what we're going to do now is, so let's say df numeric filtered is equal to df numeric, then pipe operator, we will do select. Not entirely sure if this will work with logical values. So let's say not uniform vars. So we just want to select everything that is not a uniform variable. Let's see if that works. So it can't be a logical vector. So, okay, so let's just say which do that. Okay, so this works. So we can't just say select everywhere where uniform variable is false. So what we do is we say which just returns the index of true variables. And then this little exclamation point is just saying, okay, instead of finding the true variables, find the false variables. So we're finding everywhere where uniform variables is false. And we're getting that index, and we're saying select all of those. So now we have our df numeric filtered over here, which is like 220 variables less. So we just got rid of 220 variables doing that. And that's just less features that our machine learning model has to worry about, which is good. So this ID column is pretty irrelevant to us. We're going to remove that eventually. It doesn't give any value to us. What we do need to do is do something called one-hot encoding for these three character variables. And why are we doing that? our machine learning model can't take in character strings and really digest them and say like, okay, it can't really classify them. It doesn't know how to use them. So we need to turn them into numeric values. And to do that, we'll do something called one-hot encoding.
Now, to do one-hot encoding, we're going to use another package that is called Fast Dummies. And now let's add some more comments. So here we are reading in our training data. And now what we're doing now is add one-hot encoding. So let's just call this df one-hot, and we'll say that this is dummy calls. And then we are feeding it our df. We're selecting columns. And this will be a vector of column names. So let's just go ahead and take a look what our column names are again. So we want the game rule set name, agent 1, and agent 2. Game rule set name, agent 1, agent 2. So if we run this line of code here, we're going to get one-hot encoded columns for game rule set name, agent 1, and agent 2. So if we run that and then I check the names of df one-hot, so give me all the column names. You can see here that we have, this isn't showing all of the columns, but some of them. You can see here that we have like game rule set name underscore and then whatever the rule set name is. And so in each of these columns, it's just going to be a 0 or a 1. 1 meaning it is that rule set, a 0 meaning it is not that rule set. So this just gives the machine learning model a way to digest what the rules are. Instead of doing one-hot encoding, you can just turn them into numbers, but then the model assumes there's some sort of relationship between the smaller the number and the bigger the number. For example, if 00y rules were number 1, and these rules down here were like number 10, for example, and let's say that this rule here is number 2, it's going to think there's like some sort of close relationship between these two, because there's only, if this one is 1 and this one is 2, those two numbers are a lot closer together than 1 and 10, right? So, and that's not really the case. Those two game rules aren't any more different from each other. They're just different game rules. So one-hot encoding kind of captures that more elegantly. Now, if you look over here, you'll notice that our df one-hot has 2,335 variables now. So that is a lot, and we're going to have to filter those down. But for now, we're just going to say, okay, whatever, we're going to leave it. We're going to try and build a just standard model, build something super basic, and we can go from there and kind of go back and start pruning things out and whatnot. So I'm back in what is in the training CSV. This is on Kaggle.com. I'm looking at just kind of the data description here. So as we've already seen, we have an ID column, we have the game rule set name, we have the agents, we have a whole bunch of rules. And then there's these columns at the end that are like English rule descriptions, LUD rule descriptions, the number of wins and draws for agent 1. And then what we're really trying to predict here is utility agent 1, which is going to be a number between -1 and 1. And all that's doing is basically describing how useful the first Monte Carlo simulation is going to be against the second one in this specific game for those specific rules. So if the value is closer to 1, it would mean that the first Monte Carlo simulation has the advantage, whereas if it was closer to -1, it would mean that it's at a slight disadvantage. So the reason I bring this up again is because we want to get rid of some columns here. We're going to get rid of ID column. It means nothing to us. We're also going to get rid of the rule descriptions columns. And we're also going to get rid of the number of wins, draws, and losses for agent 1, because that's basically just giving the machine learning model the answer. And we want to remove this because the number of wins, draws, and losses directly relates to the utility agent variable, which is what we're trying to predict. So if we leave these in, our model is going to be extremely accurate because it has the answers, basically. So we want to get rid of those. Let's call this df one-hot filtered, and we're going to say that is df one-hot. And then now we're just going to remove some columns. So we're going to say select minus ID minus English rules minus LUD rules and minus num wins minus num draw minus num loss
And we can split this up into different multiple lines here. So let's just enter right there. And we run this. You could see over here that is the same thing, just with 6 less variables, which is perfect. So let's check the structure of this data frame one more time. So let's just do str df one hot filtered. And I actually noticed a mistake just now from doing this structure df one hot filtered. I was noticing that our variables are all integers again when before we changed them to numeric. And it's because in this line here, when I'm creating this one hot data frame, I'm passing it the original data frame that we read in initially, when really I want to pass it our df numeric filtered, which was this one right here. So I'm going to go back and run all that, and then we'll check out the structure again. Okay, so now we have our numeric columns. Now let's just build a very basic XG boosted model. We have some setting up to do here, so we're going to load the library XGBoost. Now, typically when you do machine learning projects, you want to separate your data into testing and training data. And for us, we're going to use 80% of the data we have available for training, and we're going to test it on 20% of the data. So we need some way to split our data frame into training data and testing data. And to do that, I'm just going to create this sample.split object here, and it's just going to be sample, and the size of it is going to be the number of rows in df1 hot filtered. We just want true and false, and the probability of those is going to be 0.8 and 0.2. So 80% of these values are going to be true, 20% of them are going to be false. And I don't really know exactly why we have to do this argument here, replace equals true, but we do. I don't know why. You probably figure it out with some simple digging, but I'm not going to. So now we have our sample split. So if we can take a look at our sample split here. So it just randomly selected 80% of the values to be true and 20% of them to be false. And the length of that is the same length as our data frame. So now we can use these values to split up our data frame into training and testing data. So we'll say train data is equal to df1 hot filtered where sample.split, comma. So within the brackets here, everything before the comma is selecting rows, and everything after the comma is selecting columns. So this is saying in df1 hot filtered, select every single row where sample.split is true. So 80% of these values in sample split are true. We're just going to select all of those values. And now we can just copy and paste this. So we'll copy and paste. Now we have our test data. And it's going to be the same thing, except we put an exclamation point before sample split. So now it's grabbing all of the false values. So let's run both of those. So you can see over here, our testing data is 46,000 rows, and our training data is 186,000 rows. So we have successfully split up our training and testing data. Now, right now, our training data and our testing data actually have the answers still within those data frames. So we want to remove those. So first, let's create some objects to store those answers. So we will say train labels equals train data, and then it was called utility agent 1, and our test labels is equal to testing data utility agent 1. So now we have our test and our training labels, which are basically just the answers to what our machine learning model is trying to do. And now we want to remove those variables from our training and testing data so that the data we train on doesn't have the answers. So we'll just say train data equals train data, and then we'll say select, and we will remove utility agent. And we will do the same thing for our testing data. So let's just say test data is test data minus utility agent. So there we go. Let's run both of those. Now our testing data and training data do not have the answers within the data sets. So now we can actually generate our XG boosted model. So I'm going to say that boost is equal to XG boost. Data is our training data. Label is our train labels. We will say that we want to do 100 rounds. Say our max depth
is 6. I'm just making stuff up. Like, we're going to go through and optimize this eventually, but let's just get a model put together and just kind of see what happens, right? Our objective here is regression and squared error. So squared error is what it's trying to minimize. And if you don't really know what to use for the objective, you can do question mark XGBoost. So to just do question mark and whatever function you're trying to learn more about. And over here, it'll pop up some more information about the arguments and what they do and what your options are. So if we run this, we're going to get an error. And it's because our training data needs to be a matrix. And that's really easy to fix. We can just do as.matrix and then our training data, and boom, we go. This is probably going to take a long time to train because there's a ton of data in here. And we got another error because we have a character variable in there somewhere. So I'm just going to go ahead and find where those are. And it looks like when we did the one-hot encoding, it still kept our original columns that were characters. So we can actually just remove all of these. So we want to get rid of games, rule set, game rule set name, agent 1 and agent 2. So I'm just going to add that to our variables we removed up here. So that has been fixed, and I added verbose equals 1 here. So we should see some output while the model is training. So that ran, and I'm just going to scroll through this so you can kind of see how it goes. So it's just printing out the training root mean square error every time it goes through. So it starts off, you know, relatively poor, and it continues. It tries to improve each round. And it basically just tries to improve. You can overtrain your model, meaning that your model can be very good at predicting on the training set, but it becomes not very generalizable. So like when you try to use it on unseen data, it doesn't perform nearly as well as, you know, what you thought it would do based on how it trained. There's methods to get around that as well, and we'll kind of go back and try to fix up some of that as we go. But like I said before, we're just trying to get a base model out there, something that just kind of works. So let's continue with this. So now we have our boosted model, and we can use this now on our training set. So our predictions are going to be equal to predict. We're going to use our boosted model that we just made. And our object is going to be as matrix again. And now we are using our testing data. So boom, hit enter. And now we have a whole bunch of predictions here. And so we're going to see like how those match up against our actual values. We're going to make a data frame to kind of compare. So I'm just going to say compare df. So df compare is equal to data frame, and then we'll say actual is equal to our test labels, and our predicted is equal to our predictions. So if I run this, and now I look at df compare, we have our actual agent 1 usefulness and our predicted agent 1 usefulness. Right? So now how are we supposed to look at this and say, you know, we did well or we didn't do well? Well, the competition uses the root mean square error to determine how well your model performs. So we need to get the root mean square error in all of these values. So to do that, I'm just going to say RMSE is equal to the square root mean. And now we need the error squared. So we will do actual minus predicted, and we're going to wrap that in parentheses as well because we're going to square it like this. And I wrote this wrong. I actually just put actual and predicted in here when really these are df compare actual and df compare predicted. And so we run this, and let's just see what it is. So we do that, and our root mean square error is 0.408 on our testing data, which would be incredibly good. So if we just check the leaderboard right now, the person in first place, their code performed a root mean square error of 0.428 on the testing set, whereas our model just performed at 0.408, but that is not on the submission test data set. So there's you know, it's hard to tell without submitting our data, and I think that's probably what we'll do next, just to kind of see where we place and how much improvement we need to do to our existing model here. So this is where I'm going to stop for like the first part of this entire video series. We've built our model. Next time we'll submit this and kind of try and see where we fall, see where we lay, and then we'll come back and really try to start improving things, doing some more complex stuff. But this is a good starting point for us. So yeah, make sure you subscribe, and we'll get started on submission next time.